tests or assignments now, right?
Not now. After Ayantika ma'am ends her classes, we will have one exam of about 1.5 hours on a Saturday. Um, so we
Okay,
will
okay,
be taking our exams together. Yeah.
okay, okay, sir. Thank you.
So last day we were discussing system level analysis. We said that after we do a hardware software partitioning and we assign tasks to different hardware platforms for their execution, and we assign different types of algorithms and protocols to execute them for their execution or rules for execution on that hardware platform. We need to verify whether the performance requirements corresponding to the controller or whatever embedded system that we are designing is met. The end-to-end performance requirements are met with respect to various criteria, maybe power, area, uh, speed, and most importantly for control systems, most such performance requirements are linked to satisfying constraints on time. We took an example to see why such end-to-end timing analysis is important. And then we said that such timing analysis is difficult to achieve due to various reasons. And so the such timing analysis is difficult because the hardware platform may introduce many types of non-determinism during its execution. To increase its own performance, it introduces non-determinism. Like I told, the pipeline structure, although it increases efficiency in terms of average efficiency, but it may increase non-determinism. The cache memory structure, it is very important because it increases speed, but it also reduces determinism as to how much time an instruction will take to complete, how much time a program will take to complete. So in the face of all these non-determinisms, it is very important to um, have an end-to-end upper bound on the means worst case estimation of the performance, so that when we deploy that system actually on the field, we do not face anything unexpected. Now, we said that all that timing analysis for all this to be done, we need to have proper scheduling algorithms on the processor so that the deadlines of all tasks are met on the processor. We need to have proper scheduling algorithms on the communication medium so that the messages are sent on time to the processor, to the tasks, and the task can start on time. And this coordination between the tasks and the processor should be proper. The design, the memory design, the amount of cache memory, the amount of main memory, the type of cache memory and main memory that you put is very important to design correctly. So you need to understand have to have a very good understanding of computer architecture as well if you are a designer of memory. And then you need to have good understanding of operating systems interrupt handling, because the interrupt design for a given some embedded system also needs to be properly done, so that the end-to-end timing of the tasks that are executing on the system, for which we are doing everything that to meet the correct timing of all these tasks, do not get hampered. Now, after this discussion, we said last day that for all this discussion is fine, but for all this to be in place, we need to have a very good estimate of the execution time of a single task. So what is the time, estimation on the time a task is going to take, one task, one instance, when it executes, how much time it is going to take? Because based on that estimation of time, all other analysis is dependent on that. So then we embarked on to finding out how to determine the execution time of a single task. And we said that what happens if that execution time is not determined correctly. We said that even if there is a slight variation of what we expect an execution time to be and what actually the execution time is, maybe that whatever execution time actually happens is less than what we have expected. But even that, if it is not planned, it may result in unexpected timing of end-to-end timing of the system in the system, which we do not want. So whatever we do, the first thing, are you being able to listen? Hello,
Yes.
students, are you?
Yes, sir.
Yeah. You let me know a bit, because I am afraid, because last time I was muted. So if you do not listen to me for even 1 minute or so, or half minute or so, just let me know by telling. I often do not see the this messages, chat messages, when teaching. So we said that it is important to estimate the worst case execution time of a single task, and uh, although many a times such an estimation of worst case execution time WCET is done through simulation, but simulation does not guarantee correctness. Why? Because the simulation depends on the types and the data inputs that a program is going to take, because for each data set a program can take different control paths within its program. It may excite different if then else statements, different control paths, a combination of different control paths, different loop sizes will be taken for a given data set, and therefore it varies. So whatever analysis you do, that to be correct and formal has to be independent of the input data set. And also, many a times when you do such analysis, your platform on which the hardware platform on which the task will execute has not been fixed. So we need a mechanism for analysis which is independent of both the input data set as well as the hardware platform on which a task will execute. For that, we embark onto a mechanism called static analysis. And we said that static analysis is dependent on first the breaking of the input code into something called its control flow graph. We said that given the program, we determine its control flow graph. By the way, control flow graph is a very standard way. In any compilers, if you take the intermediate code representation, is always something called a 3-address code or its derivatives. And from there, control flow graph is easily found out. So because you have not studied, or I did not have the opportunity to tell you what 3-address code is, you may have found it difficult last day to exactly find out how do you determine the control flow graph, how do you determine the basic blocks. Although I told you the algorithm informally, but it may be difficult, it may have been difficult for you to grasp, because I could not tell you what 3-address code is. So don't bother. Just understand that such a thing is not very difficult to get, but you just have not studied that. So basically what happens is this: given any high level language like C, 3-address code is a simplified version of that. So what is that simplified high level version? 3-address code means that each instruction will contain at most 3 addresses, 2 operands and one source and 2 destination operands. So from one destination and 2 source operands. So it will do an operation over at most 2 different things and will store the result into another thing. Such simple. If you think that you have a system in which you have such simple 3-address codes, then you can easily build, you can easily get, for example, for the small program that we have here, this sum equals to 0, etc., you can build a 3-address code. From that 3-address code, this control flow graph that you got on the right side, it is very easy to get. And let us say you have that, you although you have not studied, you can understand that the logic that this small program represents, this control flow graph represents the same logic. It is not difficult for you to understand that. If you have understood that, that is sufficient for me, for us at this point in time. Now, we said that how do we go about finding the execution time? We first determine the worst case execution times of basic blocks. And for doing that, we also took the simplifying assumption that each instruction takes 1 unit of time. So if you have 2 instructions in a basic block, you will take the worst case execution time of that basic block will be considered to be 2. If you have 10 instructions in the basic block, the worst case execution time of that basic block will be considered to be 10. And what is a basic block? We said that it is the maximal sequential line of code. That means that it is just A equals to B plus C, D equals to E plus F, such simple straight line piece of code. And what is not simple? When you have branch of control. If you have if then, if you have jump to something, go to some other place, so those are branching of control. So what can't basic block contain? The instructions within a basic block cannot have, and in the intermediate instructions in a basic block cannot have an instruction which is the target of a jump. So from another portion of the program, you may have come to one line inside this basic block. You cannot have a statement or an instruction like this which is the target of a jump. You cannot jump from you cannot in the intermediate, from the intermediate statements, you cannot jump to another portion of the code. So it is just a straight line piece of code. Understanding this much is sufficient. So if you understood this, see that each of these blocks here is such a piece of code. The first two sentences sum equals to 0 and I equals to 0 will always execute. If sum equals to 0 executes, I equals to 0 is always going to execute. The rest are anyway, you don't have to understand anything deep. The rest are anyway one statements, single statements. So each of them being single statements will always execute. So these are basic blocks in itself, in themselves. So with this much understanding, we gave a mechanism, ILP based mechanisms, integer linear programming based mechanism, to find the worst case execution time of the program. So the program is represented through its control flow graph, and we want to find out the worst case execution time of the control flow graph. How do we want to find out? We first determine the worst case execution times of each basic block, and then we find out how many times each of these basic blocks can execute in the worst case. So maximum number of times these basic blocks can execute, because the execution times of the basic blocks will never change. They are taken as constants, auxiliary constants in the ILP formulation. They are constants, and because we want to find an upper bound on the number of times each basic block will run, these form the decision variables. The number of times each basic block will run is the decision variable, because these numbers can, if I give valuations to these numbers, integer numbers, I can find out the total time a certain instance of a program will take. If I tell that basic block 1 will run 3 times, basic block 2 will run 4 times, basic block 3 will run 2 times. If we give these numbers, then from these numbers, and because the worst case execution time of each basic block is known, I can find out the total execution time of the program by just summing these up. So in this slide number 9, we have found that in slide number 9, we have found that what is the worst case execution time of each of these basic blocks, and we understood that basic block 1 takes 2 units of time and all other basic blocks take 1 unit of time, because they involve just one line of code. This does not happen in practice though. If time would permit, we could have easily seen for a given general C program what is the amount of time each basic block takes, but that is not important here, just to understand how this ILP runs. Okay, so then we saw that hello, I'm getting a feedback. Can you just stop the please? Thank you. Is everybody able to hear me?
Yes, sir.
Hello. Yeah. Okay. So the time, any instance, so given the values of ni, as I told you, given the values of ni, I can find out the time the program takes, and the maximum time that the program can take over all inputs that it can have is the maximum over this. So if I maximize this as the objective function, if I take summation ci ni as the objective function and maximize this subject to a set of constraints on the decision variables, then I get the worst case execution time of the program. So this is the way in which they solve this. They find out the worst case execution time. Right. Now we said that, so the objective function is this, 2 n1 plus n2 plus n3 dot dot dot. And then we saw that this objective function will be subject to a set of flow constraints. Flow constraints means how does the control flow happens among basic blocks, and we want to have a constraints on this. The first basic way in which these constraints come is that the basic block 1 and the last basic block 7, they will execute just one time, and hence you have this 1 equals to n1 equals to e12. And we said that another important property for this ILP is that each basic block executes how many times? It is equal to the number of times control flows into this basic block, and is equal to the number of time control flows out of each basic block. So the number of times a basic block executes is equal to the total number of times control over all different paths come into this basic block, and is equal to the total number of times over all paths control flows out of this basic block. So this is the basic assumption, and this has been specified in the figure shown above. Okay, and then we said that, see, with this we said that basic block 1 is executed one times, and hence E12, which is the number of times control flows into basic block 2 from 1, is also equal to 1. So E12 is the number of times control flows into basic block 2 from basic block 1. Similarly, we understood that E62 plus E12 is equals to N2. How many times basic block 2 will execute is equal to the number of time control enters into basic block 2 from basic block 6 and from basic block 1. So and we understood that uh, we also needed to take loop bounds into consideration. Only if we consider the first and last basic blocks execute one time, we will not be able to constrain the total time. It will ultimately become infinite. So to get a finite value on the execution time, we need to have bounds on the loops. So here in basic block number 2, we have a bound on the loop which says that I will be less than 10. From that we understood that E62, E62, that means the number of times control flows from basic block 6 to basic block 2 can be at most 10 times, and hence basic block 2 can execute at most 11 times. Another important aspect which we did not talk about last day is that right. So we found that this this n3 equals to n5, n2, all this n2 is less than equals to 11. We found n2 is less than equals to 11, and we saw that therefore n3 and n5, all this is less than equals to 10, or n4 is less than equals to 10. But if we go deeper, we can see that n4 equals to 10 is still not tight. Why? Because if we get into the, means as much as we get into the program, we will be able to get better bounds. This is what this slide tries to say. For example, if we go into this basic block 3, we see that whenever I% 2 equals to 0, we get into basic block 4. From that, we can understand that basic block can execute not uh, 10 times, but at most 5 times. Because whenever I is even, only then you get into basic block 4. Otherwise, you do not go into basic block 4. So you can even have, because because we are saying that the time is given by the summation of these numbers. So so when we have n4 less than equals to 5, you get a tighter bound than if you say that n4 less than equals to 10. Right? This is what I had to say. So with this mechanism, you can get an estimation of the running time of a single task. So using a certain set of feasible values of n1, n2, n3, we have seen that we can see here that the time taken by the program for a certain valuation, I have just taken a certain valuation of these numbers, and for that one upper bound that we get for this program is 54 time units. That's all for this. Next, we shift to scheduling, which is the agenda of my current class. And in the next half an hour or so, I'll give you a brief idea of uniprocessor scheduling. Now, why am I giving this idea? Because I said that for analysis, we need to get some idea as to why we studied all this worst case execution time of a single task to do bigger analysis. But I don't have time to tell you how all types of bigger analysis is done. But at least I can give you a flavor of using this execution time of a single task. How do you order tasks on a given processor? Given that you have through hardware software partitioning, say you have decided that there are 10 tasks which will execute on processor number 1. And each of these tasks have their own demands on time. So given the demands on time of each of these tasks, how do you order the execution times of these tasks on this processor so that everybody is able to meet their timing requirements, with the assumption that you have done such a static analysis and have found out how much time each task takes for one instance when they execute on that processor. Given that estimate, upper bound estimate, you will do an analysis and find out the order of execution so that everybody can meet their demands on time. This is what we are going to study in this scheduling problem, right? And this part we have already told. Task is a sequential piece of code. Job is an instance of the task. Remember this slide, we did it in the introduction. We went through this slide number 14. If you are in slide number 14, are you in slide number 14? Hello, are you in slide number 14?
Yes, sir.
Yes, sir.
Yeah, yes. So before going into scheduling, we are trying to characterize a single task, the characteristics of a single task, based on which we will find out, given a set of such tasks, how will we order them. So with very quickly, we are trying to find out what are the different characteristics of a single task that we need to know so that we can understand scheduling. So the definition of a task is a sequential piece of code whose runtime is known to you. You know how. And rather, the runtime of each job of the task is known to you. Because what is a job? Each instance of the task is a job. And the task executes periodically. At the end of its period, it comes again and again and again and executes. Each such execution of the task is a job. And it takes WC amount of time to execute for each job. Okay. Now, you have a release time of a job. At the end of the period, the job is released. Each job has an absolute deadline, and each job has a relative deadline. And we took this example before. I'll just reiterate this. Here we have a task. This task has an execution time of how much? 1, 2, 3, 4. So WCT is 4. WCT is equals to 4 for this task. And then the task has been released. The task has been released at time 3. The task has been released at time 3. The task starts execution at time 5, but the task has been made ready for execution at time 3 for this task. The task has an absolute deadline of 10. The task has a relative deadline of 7. So 10 minus 3 relative to its release time. The task has an absolute deadline of 10, but the relative deadline of the task is 10 minus 3, 7. Okay, there can be questions from just if you are not understanding, just ask me. These are very easy things, but if you do not understand, ask. The response time is 6. Why is the response time 6? The response time is equal to the time at which the output is produced subsequent to its release. So the output of the program is obtained at 9, subsequent to its release at 3, and hence the response time of the task is 6. Okay, this is all. Now we gave this slide also I told you before, but I'll just tell you again. So what is a periodic task? Which executes a sequence of similar jobs at a very regular, in a very regular way, in a very regularly occurring frequency. At a certain frequency, completely regular, it goes on coming and executes as a sequence. So they are called periodic. I'm not going into the definition of aperiodic and sporadic. We'll not discuss that here. Periodic is the most important, by the way, for control systems. Also sporadic to certain extent. Yes. So periodic task is defined by having a period P and an execution time E. The jobs repeat regularly at an inter-arrival time of P, and the inter-release time also, you can say it's P, and the execution time is something which is between. So this is equal to the WCT, that is what you studied here already. So WCT is something which is less than equals to P, and you understand that P must be E must be less than P, because if E equals to P, that means that the complete capacity of the processor will be required to execute this task. No other person will be able to execute. So if capital U equals to 1, that means I need a complete processor. I need one complete processor. If U equals to 1, I need one complete processor to execute this task. So E by P, or utilization here, tells me what part of the capacity of one processor do I require for this task. How much resource should I reserve for this task? How much resource does this task need from my processor? This is E by P. So E by P part of one processor is required for this task, because the worst case execution time is E and the task must repeat every P. Okay. If you have understood this notion, we go into scheduling. So what does uniprocessor scheduling try to do? It attempts to solve the problem of resource contention among programs running on the same processing element, given a single processing element. So so given what we are given as input for the scheduling problem, a processor with known computation capacity that is given to us, and we are given a set of tasks whose worst case execution times and periods are known to me, deadlines / periods. Here we assume that deadlines are equal to periods because they are periodic tasks. So, and what is the output that you want? Derive an execution order of these tasks such that all jobs of all tasks can always meet their deadline. Always meet their deadlines. This is important. Okay. So with this, we come to scheduling. There are two types of scheduling algorithms. Fixed priority scheduling algorithms, or static priority scheduling, also called fixed priority. Static priority is also called fixed priority. So fixed priority or static priority scheduling algorithm and dynamic priority scheduling algorithm. Before that, we need to understand what do we mean by priority. What is priority? Priority is the relative importance of a task in a group of tasks. In given a set of tasks, what is the relative importance of this task? That means that suppose if multiple tasks are ready for execution at a given time on the processor, which of these tasks should you select? The one that is most important at a given point in time. What is most important at a given point in time is decided by the priority of this task. And we are saying that this priority can be of two types. The priority is called fixed priority or static priority if this priority does not change during execution. If the priority, relative priority or importance of a task is fixed and has been decided before execution starts, and that priority does not change at all during execution, it is called a fixed priority strategy. For that scheduling algorithm, the task system is called fixed priority task system, and the scheduling algorithm for such a task system will be called a fixed priority scheduling algorithm. Against, you understand what a dynamic priority will mean, that the tasks is the urgency of a task on the processor, how urgent a task is at a given time to execute on the processor. That urgency or priority can change during execution. If that is allowed to change during execution, then we say that the task system is dynamic priority, and we need a dynamic priority scheduling algorithm to run that set of tasks. And we will study today one fixed priority algorithm and one dynamic priority algorithm. Both are optimal. Means one is an optimal fixed priority algorithm. So what we mean by optimality, I will tell later. Let us see the algorithm first. So the first algorithm is called the rate monotonic scheduling algorithm, and it is a fixed priority scheduling algorithm or static priority scheduling algorithm. So the priorities do not change at runtime. And how do you assign priority? One basic way. Priorities can be assigned in any way. Means what do you mean by priority? How do you set the relative importance of the task among a set of tasks? That can be done in different ways. Most commonly what is done is the priorities are set according to the periods. of the tasks. That means shorter the periods, higher the frequency of execution of the task, higher becomes the priority. Shorter the period, higher the priority. So what is the highest priority task? The task which has the lowest period value, highest frequency of execution. Okay, the task with the shorter period is given a higher priority. Executes, so rate monotonic executes the task with the shortest period first. The job with the shortest period is executed next. So let us see this algorithm in execution. We are given three tasks, T1, 4.1, T2, and T3 here. Are you being able to see? Are you with me? Slide number 19.
Yes, sir.
Yes. So we are given three tasks. You see that task 1 has a period of 4 and an execution time of 1. Task 2 has a period of 5 and an execution time of 2. Task 3 has a period of 7 and an execution time of 2. So therefore, task 1 with the shortest period has the highest priority. Task 2 with the second highest period has the second highest priority. And task 3 with the highest value of the period is the least priority among all this. So next we see how this executes. So first, because task 1 and all three are available at time 0. Okay, all three tasks are available at time 0. Now because task 1 has the highest priority, all three tasks are ready to execute, but task 1 has the highest priority, so it will execute first. So this is what happens. Are you being able to see that the task has executed? Are you being able to see the change in color for task 1, which means that task 1 has executed for the first time slot?
Yes, sir.
Okay. Okay. So then next what is going to happen? Task 1 has finished. The next instance of task 1, the next job of task 1 is only going to come at time 4. So at time instance 2 means at the time 0 to 1, 1 to 2, 2 to 3, 3 to 4. So at time instance 1, so I'm supposing that the first time instance is 0. Okay, so the first time instance is 0, 1, 2, 0, 1, 2, 3, 4. Okay, so at time 1, you only have task 2 and task 3. And at that time, task 2 has higher priority. So task 2 is going to execute. Okay, now task 3 completely executes. Why? Because at time 3, again, task 2 has the higher priority because task 2 is lower period. So task 2 is executed to completion at 4. Now at time 3, and therefore task 2 starts at time 1 and completes at time 3. At time 3, task 3 is the only task available. Okay. Task 3 is the only task available. So it executes. But at time 4, task 1 arrives again. So now you have at time 4, you have two tasks, task 1 and task 3, and task 1 is of higher priority. So task 1 must be given the processor, right? Are you being able to see that task 3 could not complete task 1? Task 3 completed half of it. Why? Because it has 2 execution time. It completed from 3 to 4 and then it was preempted and task 1 executed again. Could you see?
Yes, sir.
Yes, sir.
Yes.
Okay. So then now what happens? So task 3 has not finished. Now, now at time 5, the next instance of task 2 comes again. So although you at time 5, task 1 is not there. At time 5, now T2 and T3 is there. But because T2 is higher priority, again T2 gets the processor and the T3 does not get. So T2 executes from 5 to 6. Even at 6, you see T2 has the higher priority than T3. So T2 executes again and task 3 is still not being able to complete, and therefore you have a deadline miss for task 3. Are you being able to see that T3 has missed its deadline?
Yes, sir.
Okay, so the point here is this task system therefore is not schedulable by rate monotonic algorithm. So how do you determine that given a set of tasks that this task set will be schedulable using rate monotonic or not? There are two important strategies. One is an exact strategy and the other is an upper bound, which means that if that strategy says that a given task set will be schedulable, that will always be schedulable. However, if that strategy says that, that a given task set will not be schedulable, there are still ways by which you can schedule. There may be still ways by which you can schedule that task set using rate monotony. So one is an easy calculation, which I am just going to show you in the next slide, which will give you this guarantee that if that bound that I will get in the next slide, if that bound says that yes, this task system is schedulable by RMA, you can keep your eyes closed and say that this task will be schedulable using RMA. But if they say that this task will not be schedulable, that is not a guarantee. There are other mechanisms which are more complex but will give you a guarantee. We will not go into that. So let's go into this algorithm to find bound. The utilization bound is this. A real-time system, system is schedulable using rate monotonic if the summation of utilization of the tasks, if the summation of utilization of the tasks is less than n into 2 to the power 1 by n minus 1, where n is the number of tasks in the task set and you understand, u is the utilization. So summation ui is what? Summation over ei by pi. So ei is the worst case execution time of the task, pi is their periods. Now this bound was found way back in 1973, published in Journal of ACM way back, but it is still used in many systems to design many real-time systems. Okay, let us see this bound in operation. Suppose you have three tasks. 4-1, 5-1, and 10-1. You are seeing slide number 23. Just once, please.
Yes, sir.
Yes, sir.
Yes. Okay. So what is u1? U1 is 1 by 4. U2 is 1 by 5, and U3 is 1 by 10. Right. So you have three tasks: 1 by 4, 1 by 5, and 1 by 10. So summation ui equals to 1 by 4 plus 1 by 5 plus 1 by 10. Okay, this is what is summation ui. Right. Now let us see what happens. So this is what is summation ui, and that is 0.55. And it so happens that for this case, what is the RHS? RHS is 3, because you have three tasks. 2 to the power 1 by 3 minus 1 equals to 0.78. This proof is also not very difficult, but again, I don't have time to tell you, but you can take this proof. This is a well-established proof, and because 0.78 is larger than 0.55, you can be rest assured that these three tasks will be schedulable using RMA. So even without generating the actual schedule, you can say that for this task set, if you use the rate monotonic algorithm, the algorithm that I just told, there will be no deadline misses. Okay, I don't have time to discuss any further on this, but if you have some questions, I can answer. Any questions on RMA? It is very easy, but still, if you have a question, I can answer. Quick question.
Excuse me, sir. I have a question in the previous slide.
Yeah.
Like where the deadline of task 3 was missed.
Yes.
Sir, in there, like when we get the task 1 for the second time.
I mean slide 21, huh? Yes.
Yes, in this part, like when the task 1 was attained for the second time, at that time the
Yes.
deadline was at 8, but for task 3 it was in 7. So why didn't task 3 get priority over task 1?
Because this is not deadline first. This is period first. I said that to happen, to say that the deadline is 8, what do you need to know? You need to know dynamically as to when a certain instance of a task, which means that you need to know that the second instance of the task has come at time 4 and therefore its deadline is 8. So this dynamic information you need to have. But what we are saying here is that this algorithm is a static priority algorithm. I told you at the beginning, this is a static priority algorithm. And the priorities are fixed on the basis of shorter the period, higher the priority. But this algorithm is still used because this algorithm has a nice priority with respect to the algorithm that you are trying to point out. And I'll just come next and I'll compare these two algorithms also. And why is rate monotonic still used, I will also tell you. Although the other algorithm is also told. So let's just give me some time. I will discuss the next algorithm. Is that okay? Did you
Yes.
get the point?
Yes, sir. Yes, sir.
Yeah.
Got it.
Yes. So the T1, T2, T3 schedulable under RM. Now, therefore, give for using this bound, what therefore you see is that as the number of tasks increases on the x-axis, you see number of tasks increasing, and this bound actually this n into 1 by n. So n is a very important factor here, number of tasks. You see that this n, this bound reduces to about 70% when the number of tasks grows to about infinite. When the number of tasks becomes infinite, then this utilization settles down at 70%. So you can say that given a set of tasks, any set of tasks, any number of tasks that are given to you, if the total utilization of that task set is less than 70%, then that task set is guaranteed to be schedulable using RM, rate monotony. Any number of tasks you give, this bound is told. This is a worst case bound. It's a pessimistic bound in the sense that pessimistic bound means what I told you. Pessimistic bound means that if this if this if this bound says yes, this task set is schedulable, it will always be schedulable. But pessimistic, because if this bound says that no, it is not schedulable, the task system may still be schedulable. May still be schedulable. Okay, not more on this. Let us go into the last algorithm called EDF. Okay, we'll not go. We have already seen what is response time. We'll not go into this. We'll go into the earliest deadline first algorithm in slide number 26. So whatever you were trying to point out, the last student who just asked me the question, we will see this in action in the earliest deadline first algorithm. This is the dynamic priority scheduling algorithm, which means that the relative priority of the task among a set of tasks may change at runtime. And how do you decide at runtime who has the highest priority? The task whose deadline is earliest is given the processor. The task, because all tasks have some jobs running and each job has a deadline. Given a set of tasks with their current jobs, the job having the earliest deadline is given the processor. So that is all this algorithm has. So again, it's an optimal dynamic priority algorithm. Like the other one was an optimal static priority algorithm. What I mean, I will tell you. This one is an optimal dynamic priority. What I mean, I will tell you later. Okay. So what does it say? The task with a shorter deadline has a higher priority and executes the job with the earliest deadline first. And now we are given the same set of tasks as we got for rate monotonic, and let us see what happens. So the first task executes because task 1 has the shortest deadline, 4, 5 and 7. 4 is the earliest deadline, 5 is the next highest deadline, 7 is the latest deadline. So task 1 has the highest priority and it executes. Task 2 fully executes. Why? Because when task 2 and task 3 are there, we see that task 2 has the earlier deadline even at time 3. At time 1, task 2 has the, sorry, even at time 2. At time 0, task 1 has the earliest deadline, it executes. it has just one unit of execution. Its worst case execution at time is just one, so it executes to completion at time 1. T2 has the higher priority among T2 and T3 because T2 and T3 are the only two contending tasks at time 1, and therefore it executes. And even at time 1, even at time 2, T2 and T3, when they fight, means for content, T2 wins because it has still the earlier deadline, and therefore it executes to completion. At time 3, T3 is the only task it executes. It executes, and then T1 comes again. The next instance of T1 comes at time 4, but it has now a deadline of 8 and T3 has a deadline of 7. So therefore T3 wins here. So T3 wins and it executes to completion at 5, and at 5 T2 comes, but now it has a deadline of 10. The second instance of T2 has a deadline of 10. So at this point in time T1 wins. So T1 executes, and then T5 executes, and everybody is able to complete. There are no deadline misses here. So going ahead, you understood the algorithm. If there are questions, you can ask. Otherwise, so this is an optimal scheduling algorithm in the sense that sorry, this is an optimal scheduling algorithm. In the meaning of optimality is different, but you understand here that this is an optimal scheduling algorithm at least because it allows the full capacity of a processor to be utilized. So the utilization bound you got for RMA was that complicated thing, n into 2 to the power 1 by n minus 1. Here what do you have? You're saying that if summation ui is less than equals to 1, you will be able to schedule a task using EDF, and this is the maximum that is possible because the capacity of the processor is 1. You understand, right? Because E by P is the fraction of a processor that I need for a task. If I am able to achieve utilization summation, if I am able to say that if the sum of the utilizations of my task is 1, I will be able to execute, then there can be no other algorithm that will be able to schedule a task set which has even higher load. Why? Because the capacity of the processor is only 1. There cannot be any other task set. There cannot be any other algorithm which will be able to claim that I will be able to schedule a task set which you cannot, which EDF cannot. It cannot say. Hence, it is optimal. In the same way, RMA gives the same guarantee. It says it in just a different way. You are saying it says that if RMA, there cannot exist any other fixed priority scheduling algorithm which can execute a task set which RMA cannot. There does not exist. There cannot exist. That it is mathematically proved by these people in this journal of ACM. I'll not get into the proof again. That there cannot exist any algorithm, fixed priority scheduling algorithm that schedules a task set having fixed priorities that can execute a task set which RM cannot. That is why RM is a optimal scheduling algorithm. So now you got the official definition of an optimal scheduling algorithm. What does it say? Given for a given task set characteristic, my scheduling algorithm A is optimal if there cannot exist any other algorithm which will be able to schedule a task set with the same characteristic which A cannot. So A will always be able to schedule any task set which any other scheduling algorithm for the same task set characteristic can. This is what is the definition of optimality. So let's see. It's not that so are you in slide number 32?
Yes, sir.
Yes, sir.
Okay. So let's see that EDF is not without its own problem, and although much higher resource utilization, and RM is not without its benefits. Let's see that. So under overload conditions, what happens to EDF? So EDF always executes the task with the earliest deadline first. So given these 4 tasks, so the first task has a deadline of 4 and an execution time of 3. The second task has a deadline of 5, execution time 3. the third task has deadline 6, execution time 3, and the fourth task has deadline 7, execution time 3. So in this case, the first task having earliest deadline executes. Then comes the second task. The second task, uh, now what happens, the second task can only start at 3 because there is only one processor, but because the execution time is 3, it misses deadline. Then the third task also misses deadline, and the fourth task again also misses deadline. This is called something called a domino effect of EDF. Because everybody executes the earliest deadline first, everybody misses deadline. So there could possibly be better algorithms which would leave out some of the tasks while allowing the deadlines of a higher number of tasks to be met. For example, you could have two other better schedules could be something that you see at the bottom. If you are seeing the bottom slide in slide number 32, are you being able to see the two other schedules, better schedules? Have you come to that part?
Yes.
No, sir.
Yes, yes. So see that both these schedules, instead of all trying to meet the deadlines of all four tasks, meets the deadlines of two tasks, but it meets the deadlines of a higher number of tasks than EDF does for the schedule above. So this is one problem with EDF. Why does RMA win here? Because RMA has this nice property. What does RMA say? That given a set, if you have set the priorities of the tasks offline, then RMA provides the guarantee that no higher priority task will miss its deadline because some lower priority task has taken more time than it should. If you have not understood, you can ask this question. See, in this task 1, task 2, task 3, task 4, it could so happen. Why did you allow this EDF to happen? Because it may be that this task 1, task 2, task 3, task 4, the execution times that they have actually taken in this example, they were not the stipulated execution times. These execution times have come because you did not correctly calculate the worst case execution times, which can sometimes happen because you did not do proper analysis and you overshoot your analysis. Whatever you have analyzed actually during execution, your execution has overshooted. Now if such a thing happens, if you could not do proper analysis of the worst case execution time, EDF can make your deadlines to be missed. However, RMA gives this guarantee that even if you have done a blunder with your worst case execution times, then if even if you have done blunders with your worst case execution time, however, if you have fixed your priorities before putting the system into operation, before execution happens, if you have fixed the relative priorities of your tasks, then you can guarantee during EDF scheduling that no higher priority task will ever miss its deadline due to the misbehavior of a lower priority task. A lower priority task may miss deadline due to the misbehavior of a higher priority task, but a higher priority task will never miss its deadline due to a lower priority task. And intuitively, you can understand why. Why? Because at any point in time, whenever there is a higher priority task, you give the higher priority task it's the processor, irrespective of whatever happens to the lower priority task, right? This is what you do for RM. That is why this is the last slide. Are you in slide number 33?
Yes, sir.
Yes. So there is also a nice paper 2003 Butazo which says RMA versus EDF judgment day, who wins over whom. So in this paper they say this. Finally they say that rate monotonic is simpler in its implementation, even in systems without explicit support of timing constraints, periods, deadlines. You can do, because you just know you have fixed the priorities of tasks beforehand, and you know who should execute before whom. That is known. Given a set of tasks, who is the highest priority, you just know beforehand. So even if you do not have close, means correct synchronization of time in your system, you can use rate monotony, which may be true for many simple embedded systems. predictability is higher for predictability for the highest priority task is always guaranteed. That means if higher the priority of the task, higher it is predictability, because these higher priority tasks cannot miss their deadlines due to a set of lower priority tasks. On the other hand, EDF allows full resource utilization. And however, it exhibits misbehavior during overload conditions. This is all of my section with you for this course. Hope you liked it. We will take one class test at the end, after Ayantika ma'am finishes her part of the course, we will take one class test. Thank you. Any questions? Any questions? Did you more or less like what I said? Could you understand what I tried to explain? Yes, no?
Yes, sir. Yes, sir.
Okay. This yes, sir, is a thank you for me. Bye.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. Thank you, sir.
Thank you, sir.
Welcome.